Now let us see more about searching lists and keeping them sorted. As far as searching in a list is concerned, let us suppose that the list is stored in an object of our data type list. Okay, this is the list, and we wish to find whether a specific element is in this list or not, and if it is there, then where it is, the location. So let us assume that the list is implemented such that you can easily access any element just by taking this theta of one time. And the first approach, this approach is quite simpler. If we use a linear search and use a for loop, and we start from the beginning of the list, we run until the end, until you actually get the element, and we try every index in this list. So the time for this will be around order of n for a list of length say n, and we have to do at most a constant amount of work for each element. For each element you have to go for that constant element or time, constant element time. So this will be omega n in the worst case if the element is last, and we may actually have to go through all the elements to understand the element whether it is in the list or not. Even if the element is not there, you have to search for each element till the last. So even if the element we are looking for it is just in the second half, like in this half, if we make it two half, we'll still have to go through this first half, which will still be omega of n. So in totality of our discussion, the algorithm will be theta n. We started with this theta 1, and then omega n, what we are saying, even after finding that the element is not there, we have searched, or we have gone to this omega of n. So this is not seemingly very good, but if the items are unordered, they are not in any sorted order, we cannot do anything. There is not much else what we can do. But if the elements are in a list, say for example you have integer or strings, and if they are sorted means they are in ascending or descending order, then we may easily apply this binary search. Binary search, the initial condition should be the element are sorted. And since we have talked about binary search, this will be very intuitive for you. For example, we start with the median of the element, and if that element is found, we are done. Otherwise, we take the left. If f is x, for example, if this is the list, and we come here and the median value, we could not find the element. If we found the element, we'll stop it here only. But if the element is smaller than the median element, because this list is sorted, we'll search in this half, otherwise in this half. Again, we analyze the running time of binary search with some caution, that how many steps have we taken, because every time we are checking at the median, the remaining array is at most half as big as the current array, right? And sometimes we may get lucky and we can find the element right away, but this is not we are finding out. We are actually interested in the worst case here. And if because we have already talked about binary search, you know that the clear sign of running time is order of log n. How this order of log n comes? Because if we apply this divide and conquer method, then every time we are making things half, means say for example if this is 16, just divided by 2 we'll get 8, then divided by 8 divided by 2, because we are making it half, so it will be 4 divided by half, so we are making it 2, and just divided by half it will be 1. So there are around how many steps being taken? So you take log of 16 and you straight away realize that how many steps you have taken? 1, 2, 3, 4. So 2 to the power 4 is 16. So this is just for 16, but for all the other numbers, you will get the order of log n. This is how log n has come. Log 16 we take 2, so it will be 4 steps. But hopefully you are experienced now how we for divide and conquer, basically which we divided half, the running time will always be log n, order of log n. But we will try to derive the exact formula. How? Let us take Tn as the worst case running time of this binary search, which we assume to be an array of size n, and we'll use a recurrence relationship for this running time of binary search. This will be 1 plus Tn by 2, and T1 will be 1. This is the outward condition or bottom outward condition. Because we are making it half every time, but we start with 1. That is why this is 1 plus Tn by 2. We always spend one step or a constant number of steps for looking at the median element. So this is for, we have 1. And if we are unlucky, we recurse we have to check another array whose size will be n by 2. So this is, for this we have this Tn by 2. This is for finding median, and this is Tn by 2. So actually that takes Tn by 2 by definition. And the most precise would be, we can replace Tn by 2 by this is what we call as ceiling and floors. So Tn minus 1 by 2. This is just to make sure that all the elements which are should be integers. And we have already experienced that running time analysis tells us that rounding up or down means ceilings and floors is not at all crucial as far as running time analysis is concerned, because the numbers are so large. 6.5, if you take it as 6 or 7, it doesn't matter actually. So at this particular point, we would think that whether we could perhaps be better off by not checking the middle point, but say 3/4 or 1/4. And if we actually perform that, and where the element is on the smaller side, it would be quite better, because we have just taken the point as 3/4. But there is another discussion for this. If the element we are looking for is in the larger part, we would spend more remaining time, see T3n by 4. So we are, as a computer people, we are trained to be pessimistic about this kind of thing, because we actually want the worst case. When we find out the worst case, the user will always will get the best case. So we need to analyze the worst case under this assumption, and we will make the recursive call on this array of size 3n by 4. And this inequality we have just seen, where T1 is equal to 1, this is the outward condition. It captures the running time of binary search quite precisely, but it does not actually provide us with the formula that we can easily use to get a feel for this running time. So we would like to have a closed form solution, that is one without our recursions or sums. So how to do it? Let's unroll or elaborate the recursion in few steps. Tn is what we had is this 1 plus Tn by 2 will be, Tn is less than, or this is greater than Tn, and it will be always greater than 1 plus Tn by 4, and then 1 plus 1 Tn by 8. So we are just trying to divide it, which will actually happen in binary search. So to do this, while doing this unrolling, we should notice that we occur a 1 for every time. 1 plus 1 plus 1 plus 1. We have the array size. So for k steps, which means adding k times the number 1, the remaining array size is n by 2 to the power k. And the recursion is going to stop when the array size is 1. That is, we stop unrolling when n by 2k 2 to the power k is less than or equal to 1. And when we solve this for k, it is when it is guaranteed to stop, we say that k, we just take the log both sides. So since k is greater than log n, right? This is how we achieve this log n. Since each iteration does a constant amount of work, we can come up with saying just that Tn will be this theta of log n. Our guess was quite right, and it actually provided us the good reasoning. But we need to provide or a proper proving it by formal nature. So anytime you prove anything about an algorithm that involves recursion or a loop, that is for or while, it is always a good idea to do it using an induction. And this case also we can use induction. So let us start. We need to be cautious and careful. For example, if we have n equal to 1, the result will be this theta of 0, which says that it takes no time. So we need to amend this. We have to see that Tn should be less than or equal to log n plus 1. So our base case n equal to 1, T1 will be constant, no problem with that. We'll just treat it as 1, and the right hand side will be this T is 1, we say it as 1 because we already taken T1 will be equal to 1. This is our ending condition. And the right hand side, log n plus 1, we place 1 here, log 1 will be 0 plus 1. So the base case work for induction. And for the induction step, we have to do for n k or k plus 1, say k n or n plus 1. We are expressing Tn in the form of Tn minus 1 by 2 rather than Tn minus 1. So the regular induction approach doesn't work here. With the simplest way around is to use a strong induction instead. How? The strong induction hypothesis will state that for all which is less than m, we have Tm is less than or equal to 1 plus log m. We have just taken this m. In induction books we have seen this, we take k and prove it for k plus 1. So what we have to prove? We have to prove Tn is less than or equal to 1 plus log n for all m which is less than n. Just not doing this k and k plus 1 stuff. We are saying we have m and n, and for all m, n should also be there to get used to the strong induction hypothesis for any numbers which is m less than n. So what we know about this Tn, we know that Tn is less than or equal to 1 plus Tn minus 1 by 2. This we have already discussed. So we can check regardless of whether n is even or odd. For n minus 1 by 2, it should be less than n. And we can then apply the induction hypothesis to n minus 1 by 2. So it gives us Tn minus 1 by 2 is less than or equal to 1 plus log n minus 1 by 2. And if we apply the logarithmic policy, we can rewrite the right hand side of this equal to log 2 n minus 1 by 2, which is less than or equal to log n always. And now plugging this, we get Tn is less than or equal to 1 plus log n as what we wanted. So this is actually our induction step using strong induction hypothesis. We can also use induction to prove that binary search is actually correct. In particular, that is always it always finds an array element that is actually in the list. We'll get it to the time constraint, but we can actually find out that the condition where the values are not coming. Then the important search which we will be discussing is interpolation search. We have seen binary search. Then what is this interpolation search? We have already discussed about finding or searching in a phone book. So we don't exactly perform binary search in phone book. For example, we are looking for some Mr. and Mrs. algorithm. We'll not start with middle. Do you start in your phone book to find in the middle? No, you start with the first entry. So we know the range of entries to expect, and that suggests that the entry is likely which is close to the beginning, so we look immediately close to the start, because algorithm A start with A, so we don't find it on the page. For instance, because we found Mr. Boole instead, we will probably go about 1/3 of the way from the beginning to the current page, because by far we know that in phone search or phone book directory where to get what thing, because they are arranged. But here we would be executing the interpolation search. How does it work? We need to assume that there is some sense in which the entries can be translated into integers. So we do some basic arithmetic. So suppose assume that we are left with only an array ALR. This is left, this is right. L and R are left and right endpoints, and we are looking for an entry X. So the range of entries, which is between AL and LR, if things were evenly spaced, we would expect X to be about a fraction X minus AL by AR minus AL into the array. Those people who are aware of interpolation, they know how to find out interpolation position. So that is why the next search at position will be, the M will be L plus R minus L and X minus AL by AR minus L. And we will recurse just like the binary search. So we have to find M every time using this relationship, and then just by applying our idea of binary search, we can do it. In fact, the interpolation search is exactly the same code as binary search, with the exception of computing a different M instead, not the median. If you are assuming M to be median, then the interpolation search will be actually equal to binary search. So interpolation search zooms in much faster on the part of array X, which is like where X is likely located. And we can also prove that if the elements of the array are roughly evenly spread, the interpolation search find X in order of log n step, which is much faster than log n. But we have to notice that it only works when the elements are evenly spread. For evenly spread we have this, and uneven spread it may become worse. So it's not very difficult to construct somewhat weird inputs in this interpolation. And search does no better than the linear search if they are not evenly spread. In that it will scan for array from left to right, and those instances, they contains a cluster of lot of people whose names start with same letters in our phone book. So hope you got the idea of interpolation searching. And what about keeping our list sorted? So in order to reap all those nice benefits of, say, binary search and even interpolation search, so we need to make sure that the remains, whatever is there in our array or list, it should remain sorted all the time. Earlier, our list type had functions, say set, setting in the position, getting, inserting and removing. So nothing needs to change for get, of course, in this particular case. And for remove, in this get we don't need to change anything. For remove, it also makes sense to just remove the item at position POS which is given. That will not cause the list to become unsorted. The function set, which is this, really does not make sense to have. Why? If we choose to override an element, then how do we guarantee that the result is sorted? Because we want our list to be sorted even after doing all this stuff. So, we should just not be allowed to override. So it doesn't really make sense for us to be allowed to insert an element at a position of our choice. But there has to be some other discussion to this, or other statement. We should have a function insert sorted, which will find the right place to insert the element by itself. So you want to see how long it takes to perform the sorted insertions and subsequent lookups and searches. So if we use an array, then we use this binary search to find the place where we where the data should go. This in binary search we know that it will take order of log n time. But after that we have to shift or copy the data to make a room for that insertions also. That will again take theta of n times. If this is the list and we find that okay, our value should be inserted here, we have to shift these element, and every time the element needs to be inserted in the first half of the array, we need to do all these things. So unlike or using a linked list, inserting an element is the right position only take order of n once we know the position. So by far these linked lists we can see. So but finding the right position, it again it is taking theta of n. And the reason is that to get a function is really slow on linked list, because we need to scan linearly, because it is actually linked list. So to read the position I, it takes again theta I position. We have already seen in earlier lecture. So linear search is actually the better choice to find the right position, and sorted insertion take theta of n, just like arrays. So what we are getting in return? Absolutely, we are getting nothing actually, because to get a function takes theta of n, and if we are to implement this binary search on top of our linked list implementation of this sorted list, it will take again theta n for each step of binary search, which would give a total of n into log n, that is theta log n. So binary search is much slower than linear search, and this is absolutely no point in implementing it on linked list. For these reasons, there is also pretty much no reason to keep a linked list in sorted order, right? But we'll see in that more elaborate version of linked list called skip list, which actually does justify a sorted linked list. So this is how we can keep our things sorted, and we have already introduced and also introduced your interpolation search and talked about various aspects of our binary search. Thank you so much.